Hello everyone, welcome to another episode of Math-321. So today we're going to do Investigation 28, which is products of groups. Okay, so here are the focus questions for the lesson. So what is a direct product and how can direct products be used to construct larger groups from smaller ones? What is the external direct product of two groups and how is the operation in an external direct product defined? How can we find the order of an element in a direct product of groups? What is an internal direct product of groups? Under what conditions is the internal direct product defined? How are the external and internal direct products of groups similar, and how are they different? Okay, so you guys already know that you can combine two numbers in a lot of different ways in order to make another number. Well, you can actually do the same thing with groups. You can combine them in various ways to make another group. So one way of combining groups is through their direct product, and that would contain both of the groups you combined as subgroups. But before a formal definition, let's just look at a small example in the next activity. And before I show you this activity, I want to just remind you that the Cartesian product of sets R and S is all of the ordered pairs, where the first element comes from the first set, R, and the second comes from the second set, S. So in other words, the Cartesian product, it's notated like that, and it's these ordered pairs, little r, little s, where little r is from big R, and little s is from big S. Okay, so here is your preview activity. So go ahead and pause the video and do this activity, and then I'll go over the answers. Okay, so let's go over the answers here. The direct product of Z2 and Z3 is denoted like this, Z2 and then the circle plus, and then Z3. Its elements and operation table are shown above. So part A, describe precisely how the elements of Z2 so I'm going to read that aloud as the external direct product of Z2 and Z3. I don't actually know how that symbol is meant to be read aloud, so I'm just going to read it like what it is, which is the external direct product of Z2 and Z3. Describe how those elements are related to the elements of Z2 and Z3. Okay, so if you look at the table here, the elements in that external direct product, they are listed here and also up here. So if you look at those, I hope that you can see that that is just the Cartesian product of the two sets. So the elements are those in the Cartesian product. So just to flesh out that answer a little bit, this is, we'll call it like A sub 2 and then B sub 3. So those are elements that are in Z2 and in Z3. Okay. And then for part B, how does the operation in the external direct product of Z2 and Z3 seem to be related to the operations in Z2 and Z3? Okay, so let's just look maybe at a couple of examples here. So for example, how do we do the operation between 1 sub 2 and 1 sub 3 and 1 sub 2 and 1 sub 3 again? So if we look at the result there, we're getting 0 and 2, and it looks like what's happening there is that you're just adding the first two elements in Z2, so 1 plus 1 in Z2 is 0, and then you're adding the other two in Z3, so 1 plus 1 in Z3 would be 2. So it certainly looks like from that example that that's what's going on. We could look at a couple of more examples, maybe like 1 and 2 and 1 and 0. So we're getting 0 here for the first part, which would be 1 plus 1 in Z2, and then we're getting 2 for the second part, which is 2 plus 0 in Z3. So it certainly does look like that is what is going on. So it seems like when we add, let's say, A sub 2 and B sub 3, and then we do plus, since the operation here I guess is addition, C2 and D3, we get that we just add the elements in the first group like this, and then we just add the elements in the second group like this. Okay. So part C, does the external direct product of Z2 and Z3 seem to be a group under the operation given in the table? If so, what is the identity element, and how could we find an inverse? Okay, so in terms of whether it looks like a group, I'm looking for the Sudoku effect. So in other words, does each element appear exactly once in each row and column? Is that here? So if I look at the table, I think I do see, yeah, that there's no repeats within any rows or columns. So that would indicate that it is a group. And then how would we find, or sorry, what is the identity element and how would we find an inverse? So the identity element, so I'm looking for a row and column that are the same as the ones on the very left and the very right. So it certainly does seem like this row right here, or this column right here, is the same as this one. So that would indicate that the identity would be this. And similarly, it does seem that this row right here is the same as this row up here. So that would also indicate that this right here should be the identity. So the identity seems to be 0, 0, which kind of makes sense because we're working with addition here, so the identity should be 0. So having zeros in both places would make sense with the operation we looked at on the last slide. And then how would we find an inverse? So inverses should then, if it's just really just element-wise addition, then inverses should be just like the negative of both elements. So in other words, we would just make both parts negative. Oops, I meant to put the negative inside, like this. And then, of course, to actually find the negative within a modulus group, you might have to add the modulus a couple of times. Like, for example, if we wanted to know the inverse of, I don't know, 1, 1, then we do the negative on both parts, and then negative here too. Oops, not a 1, not a 3. A 1 there and a 3 there. And then that would, of course, be the same as putting the negative inside of the brackets. So I'm just moving these negatives around. And then you can always add the modulus to whatever's in the brackets there. So this would be the same as if I add 2 here, then I would get 1 there. And then if I add 3 to the other one, I would get 2 here, since they have different moduluses. And we do see that the table shows that 1, 1 plus 1, 2. Oh, there's so much notation here. Oops, 2. Let's just check that in the table. So here's 1, 1, and here's 1, 2. And they do give us 0, 0, which is the identity. So that's good. So it does all kind of work like it seems like it should. Okay, so part D, consider the set S defined by S equals, okay, so this is all the ordered pairs where the first one is 0 and then the second one can be anything. Is S a subgroup of Z2, external direct product of Z2 and Z3, and why or why not? Okay, so let's just find where these elements are in the row and column on the very left and the very top. So that's going to be these ones right here that I've circled. And if you look at their operation table, just that small part that corresponds to them, do we see the Sudoku effect in there? Is everything appearing exactly once in each row and column? So it does appear to me like the Sudoku effect is working on S. Oops. So that will be a subgroup. Yep, so that's my explanation. And then, of course, that, the Sudoku effect working means that it'll be closed. it'll contain inverses because you can find whatever product, you can find the inverse in each row and column. That means you'll be able to find, or sorry, you can find the identity in each row and column. That means you'll be able to find an inverse. And we can't really check associativity. It has to inherit that from the larger group. And then the identity is in there as well. So yeah, it should be a subgroup. And then what is the relationship between Z3 and the set S defined in part D? So the set S defined in part D, it sure resembles Z3 very closely. It has 3 elements just like Z3 has, and it's kind of like you've just taken Z3 and you've like decorated it with this extra 0 appendage that is just kind of like pasted onto the left side of all of the elements in Z3. So it basically is Z3. It behaves and looks almost exactly the same. So it pretty much is Z3, but just with this thing, 0 to stuck onto all the elements. That doesn't look like stuck. Let me rewrite it. Okay. Yep. Okay, so now let's look at the actual definition of external direct products. So definition 28.2, let G and H be groups with operations. So the operations are written like multiplication, and then we've put a little subscript onto each of them with the name of the group, because they could actually be different than multiplication, and they could be different than each other. So we're going to call these operations .G and .H respectively. Then the external direct product G of G and H is the Cartesian product G cross H, like this, together with an operation defined component-wise. In other words, the operation works like this. So if I want to multiply 2 of these ordered pairs from the Cartesian product, then all I do is I just multiply the ones from G using the operation from G, and then I multiply the ones from H using the operation from H, and then I just put them in the ordered pair like that. So it's pretty straightforward actually, and it's exactly what we were doing on the last activity. So I will say here that we typically don't actually use the subscript G and the subscript H notation for those operations, because it's just kind of too clunky to be dragging around, and also because we don't really need it. You can understand which operation is being used in context. So in other words, if you have 2 elements G1 and G2 from G, and you have 2 elements H1 and H2 from H, then when you see those G elements being multiplied together, that means you're using the G operation. And if you see the 2 H elements being multiplied together, that means you're using the H operation. So you use the operation that is for the group that the elements came from. Okay? And likewise, if you see the ordered pairs being multiplied together, then you're using this definition here for the operation that we saw in the definition just now. Okay, so you just have to figure out what the operation is in context. I should also note that neither this notation nor the terminology for the external direct products are set in stone. So different authors use different words and symbols. Even if you go on Wikipedia, you can see they're using different words and symbols on there. So some authors use this cross product notation here, the cross or the times symbol, to refer to the external direct product, and some authors only use this circle plus thing when G and H are both abelian, or when they both have the group operation of addition, because it kind of looks like addition. So it's people are all over the map on what they're using, so you just got to be sure when you're reading some other textbook or Wikipedia or whatever that you understand that there might be different notations, and there could even be different vocabulary. Like they might not even call it the external direct product, they might call it something else. So you just have to be careful. Okay, so let's do another activity, activity 28.3. Go ahead and pause the video and give this a try, and then we'll go over the answers. Okay, so let's go over the answers here. So first of all, list all of the elements in Z2, external product of Z2 and Z2. So the elements here are going to be from the Cartesian product. So the Cartesian product is going to be the following. So let's see, we're going to have 0, and then 0 again, and then we're going to have, I should put that in a set, and then we're going to have 0 and 1, and then we're going to have 1 and 0, just doing them in alphabetical order, and then we're going to have 1 and 1, and that's all of them. Okay, So part B, construct the operation table for this external direct product using the operation that we went over on the last slide. Okay, so it's not a very big table, so I think we can do this hopefully not too time consuming. If you want to just fast forward and look at the end product, that is totally fine. In fact, maybe I'll just drop these subscripts because they're kind of making it take longer. Okay, so that was just the row and column labels. Okay, so let's go ahead and do this. So when we're adding 0, 0, of course, okay, I'm going to drop them for the inside here. It doesn't do anything. So this is just going to be copying down from the row above. And remember, we are doing the addition operation here, even though on the last slide it was talking about multiplication, but because this group is additive, we're doing addition. Z2 and all the Zn groups are additive. Okay, and then this column here is also just copying over. Oops, mix those ones up. Okay, and now we have to actually think a little bit. So we're doing element-wise addition again. So 0 plus 0 is 0, and 1 plus 1 is also 0 in Z2. So 2 is 0. And then 1 plus 0 is 1, and 1 plus 0 is 1. Okay, and then 1 plus 0 is 1. 1 plus 1 is 0. Okay, 0 plus 1 is 1, and 1 plus 0 is also 1. Okay, and then let's see, 1 plus 1 is 0, and 0 plus 0 is 0. 1 plus 1 is 0, 0 plus 1 is 1. Okay, 0 plus 1 is 1, and 1 plus 1 is 0. 1 plus 1 is 0, and 1 plus 0 is 1. And then finally 1 plus 1 is 0, and 1 plus 1 is 0. Okay. Okay, so here is another activity for you, and hopefully you can see that this is going to lead us up to part E, showing that this external direct product is actually a group. So go ahead and pause the video and try this one, and then we'll go over it. Okay, so let's start with let G and H be groups, and part A, why is the external direct product of G and H closed with respect to the operation defined on the direct product? Okay, so to show that it's closed, we need to take two elements from this external direct product and show that when we multiply them, it'll still be in the external direct product. Okay, so let's let's call them G1, oops, actually, let me do it like this. Let's call them X1 and X2. So let this be two elements that are in this external direct product. Okay, then because they're in there, that means that X1 has to actually be some ordered pair like this, G1, H1, and X2 has to be also an ordered pair. We'll call that G2 and H2. Okay, where G1, G2 are in G, and H1, H2 are in H. Okay, then if I multiply X1 and X2, what happens? I'm just going to do this element-wise, so this is going to be G1, G2, and H1, H2. Okay, then because G and H are closed, that means that G1, G2 is in G, and H1, H2 is in H. That's not a very good in symbol. So that means that X1, X2 is in this external direct product. of G and Okay, so part B is the operation defined on the external direct product and associative operation. Prove your answer. Okay, so let's give this a try. So I'm going to let x1, x2, and x3 be in the external direct product. Okay, so then x1 equals g1 h1, x2 equals g2 h2, and x3 is going to equal, I'll just call it g3 and h3 for some elements, g1, g2, g3 in G, and h1, h2, h3 in H. Okay, so now let's try doing the multiplication with both types of parentheses. Okay, so we're going to do, let's do x1, x2 together first, like this, times x3. Okay, so first we need to evaluate x1, x2. So this is going to be g1, h1, g2, h2. Okay, and then on the outside here is going to be g3, h3. Okay, so I'll do the part inside the parentheses first. So this is going to give me g1, g2, h1, h2. Okay, and now I can combine that with, multiply that with g3, h3. So this is going to give me g1, g2, g3, h1, h2, h3. Okay, and then if I want to, I can separate that back out like this. So I can take g1 and h1 away at the front. Be careful because this is not necessarily abelian, so make sure you're keeping this in the right order. And then I'll have h1, oops, not h1, h2, h3. Okay, and then I can split that last part back out like this into g2, h2, g3, h3, like that. Okay, so it is associative. Okay, part C, is there an identity element for the operation defined on this external direct product? So let's call the identity elements, we need the identity elements from G and H to do this, and then it's just going to be the ordered pair with those two. It's not very complicated actually, it's kind of obvious. That's what it should be. So we're going to let that be the identity element of G, and the one for H we'll call it E sub H, be the identities in G and H. Okay, then consider this pair. So I'll just call it E. So it's going to be the ordered pair with EG and EH. So let's let there be, so to show that this is the identity, let's take some element from this external direct product of G and H. So X is G comma H for G in G and H in H. Okay, then what happens when we multiply E times X? We're going to get EG, EH times GH. So that is going to just be GH, or I guess I can do an intermediary step here to make you feel more comfortable. So EG times G and then EH times H, and that'll just be G and H. And then if we do it the other way, XE, that's going to be the same way. Oops, not G. So this will be G times EG, and then H times EH, and then that'll just be G and H. Okay, so E is the identity. Okay, so now let's look at part D. Does the element GH in the external direct product of G and H have an inverse? Okay, so just like we did for the identity, we're just going to use the inverse of little g and little h. Since G and H are groups, we have G prime in big G, and we have H prime in big H. Those are elements that exist. So G inverse H inverse is in the external direct product. Then if we multiply these together, so GH times G inverse, H inverse, we're going to get EG and EH, which is the identity for the direct product or external direct product. And also, if we do it in the other order, we'll still get the identities. And that is our identity element for the external direct product. Okay, so this brings us to part E. Is this external direct product, is it a group under the operation defined? Yes, so we did closed, we did associative, we did the identity, and we did inverses. So it has all of those four group properties, and so it is a group. Okay, let's look at a couple of theorems. So theorem 28.5, let G and H be groups, then the external direct product of G and H is also a group. We just proved that. And the second theorem here, let G and H be groups with identities EG and EH respectively. Then the external direct product of G with a set containing just the identity from H. And so if you want to think about what that actually looks like, it's all of these ordered pairs where it's little g in big G, and then the second element is just the identity from H. And likewise, this set that just contains the identity from G, external direct product with H, so that is all of the ordered pairs with the identity from G and then something from H. Those are actually both subgroups of the external direct product G plus H, or G of G and H. Sorry, I'm still having trouble pronouncing that symbol, or not pronouncing it rather. We're not going to prove this. I think it should hopefully be pretty obvious to you that these are going to be subgroups because they're going to satisfy all of the group axioms. Because whenever you do an operation with more than one element in either of those subgroups, it's just going to act, just the two elements from G or just the two elements from H will interact, and then the other part will just stay the identity. So it will be closed, it will have inverses, it'll be associative, and it'll have the identity. I hope that's pretty obvious. So note that even though this external direct product here of G with the identity from H, it doesn't exactly equal G because they have different elements. One of them has ordered pairs and one just has regular elements. But we can actually identify the elements of this external direct product with the elements of G in such a way that these two things actually are basically the same. They're basically identical. In a technical sense, they're what we call isomorphic, although we're not going to get to what that word means until a little bit later. So in other words, what I'm saying is we can identify each element, little g, and the identity from H in this external direct product of G with the identity from H. It's going to actually behave exactly the same way as the element G behaves in the group G. And so in that sense, there's basically a copy of the group G within the external direct product of G and H. And likewise, there's also a copy of H in this external direct product of G and H. Okay, so these little groups here, the external direct product of each group G and H with the identity from the other group, that is basically a copy of that group. So that's kind of interesting. So in that sense, the external direct product of G and H contains G and H as subgroups, although they're not exactly G and H, but they're copies of G and H. Okay. Okay, so here's another activity for you to try. So go ahead and pause the video and do this, and then we'll go over it. Okay, so if you've done the activity, then let's go over it. So if G is a group of order m, that simply means that G has m elements, and H is a group of order n, that means H has n elements. What is the order of the external direct product of G and H? So remember, the order is just the number of elements in the group. That's when you're doing the order of a group. Of course, if you're doing the order of an element, then it's the number of elements in the cyclic subgroup generated by that element. G external direct product with H is the elements here are from the Cartesian, that's not even a word, are from the Cartesian product. of G and H. So the number of elements in the Cartesian product is just simply the number that are in G times the number that are in H. It's not very complicated. And that's it. Okay, so you can learn a lot about a group by understanding its cyclic subgroups. So for groups G and H, with little g in G and little h in H, does the order of the element GH equal the order of G times the order of H? So we're going to find out in this activity. So go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go over this. So determine the orders of the elements 4 in Z8, 3 in Z12, and then the ordered pair 4 and 3 in the external direct product of Z8 and Z12. Okay, so for 4 in Z8, we're looking again at the order of the cyclic subgroup that is generated by this element. So let's see what actually is that cyclic subgroup. So it's going to consist of, so it'll have 4, and then it'll have 2 times 4, which is, that's actually 0, right? Because that goes to 8 and then it comes back to 0. So once you've gotten 0, you can stop. That'll be the last one. So this is just going to be 2 different elements there. And then the order of, the order of 3 in Z12. There's too many little signs here. 3 in Z12. So let's see what is in this cyclic subgroup. So there's 3. And then there's 2 times 3, which is 6. And then there is 3 times 3, which is 9. So we're doing integer multiples here and not powers, because this is an additive group, of course. And then we're going to do 4 times 3. So whenever it's addition, you do multiply by integers instead of raising to integers. And that is going to be 0, so we can stop there. And so this is going to be 4. Okay. And now let's determine the order of the cyclic subgroup generated by, oh my gosh, there's even more symbols now. Okay, there's 4 of them. Okay, let's determine the order of the cyclic subgroup generated by this ordered pair. So let's see, what is going to be in this cyclic subgroup? So first of all, there is the element itself, which is 4, 8, or sorry, 4, 3. Okay, and then there's 2 times that. So if we do 2 times this element, what do we get? So I think that's just going to be, so the first one's going to be 0, right? We saw that before. And then the second one will be 6, which we also saw before. Okay, next element that's going to be in here is going to be 3 times this ordered pair. So we didn't come to 0 yet, so we're not done. We have to keep going. We didn't come to 0, 0 anyway. So that is going to be, okay, so 3 times 4 is 12, and then mod 8, that is 4. So that'll be 4, 8. And then 3 times 3 is 9, so this will be 9 in modulo 12. Okay, so we still haven't come to 0, 0, so we have to keep going. So 4 times this ordered pair is going to be, I have a bad feeling I'm going to need to do this 8 times. Okay, let's just keep going. So this is going to be, okay, so 4 times 4 is 16, mod 8, that is 0. And then the other one will be 4 times 3, mod 12. Oh, nope, we did it. Okay, this is 0 also. Okay. That's mod 12. Okay, so this is, and then I'm doing the order of that. So this is 4 different elements. Okay, so the order was not 2 times 4, it was actually 4. All right, interesting. Okay, let us try another one. So determine the orders of the elements 4 in Z8 and 4 in Z12. So we already found out that 4 in Z12 or Z8 was, there you go, okay, is 2. So now let's do what is the order of 4 in Z12. So this is going to be the order of the cyclic subgroup generated by 4 modulo 12. So this is going to contain, first of all, 4, and then 2 times 4, I won't write that out, but that's just 8. And then 3 times 4 is going to be 12, which will be 0. Okay, so once you get to 0, you stop. So this is going to be, the order is the number of elements in there, which is 3. Okay, and now let us do the order of the cyclic subgroup generated by this ordered pair of 4 and 4. Okay, so what is in this cyclic subgroup? So the first thing is 4, 4. And then the second thing is going to be 2 times that. I think I'll just, to make this a little shorter, I'm just going to go ahead and do the 2 times part in my head. So this will be 2 times 4 is 8, which is 0 in mod 8. And then 2 times 4 is 8, which is 8 in mod 12. Okay, and then the next one, so 3 times 4 is going to be 12, which is going to be 4 in mod 8. And then 3 times 4 is going to be 12, which will be 0 in mod 12. Okay, so we have to keep going because we haven't gotten 0, 0 yet. So the next one will be 4 times 4, which will be 16, which is 0 in mod 8. And then 4 times 4 is 16, which is 4 in mod 12. Okay, and then 5 times 4 would be 20, which is 4 in mod 8. So the first part just keeps going back between 4 and 0. So 8. Okay, and then 5 times 4 is 20, which is 8 in mod 12. Okay, let's keep going. Hopefully this one is 0. Okay, and then 6 times 8 is, 6 times 4 is 24, which is 0 in mod 8. And then 6 times 4 is 24, which is also 0 in mod 12. Okay, so we do get 0, 0 eventually, and then so we can stop. And so the number of elements in there is actually 6. So in this case, we saw that it was the product of the 2 orders. It was 2 times 3, which is 6. But in part A, it was not the product of the 2 orders. Okay, so this brings us to a theorem, and before you read this theorem, just note that this LCM of A and B, that notation, that stands for the least common multiple of A and B. In other words, the smallest positive integer that is a multiple of both A and B. Okay, so theorem 28.9, let G and H be groups with little g in big G and little h in big H, and both of them of finite order. In other words, both little g and little h are of finite order, not necessarily the groups. Then the order of the ordered pair, G, H, will be the least common multiple of the order of G and the order of H. So that is actually what we saw in part A of the last activity. The 2 orders of G and H were 2 and 4, and then we saw that the order of their ordered pair was 4, which is the least common multiple of 2 and 4. So the full proof is in the textbook, but the basic idea of the proof is that when you raise this ordered pair GH to a power, that will only give you the identity in the external direct product, which will be the identity for both groups in an ordered pair like that. You'll only get the identity from raising G, H to a power if and only if that power is a multiple of the order of G and of the order of H. So that's just because whenever you raise G to a power, it'll only give you the identity if the power is a multiple of the order of G, and then the same is true of H. So of course, to get the identity for both, it has to be the power must be a multiple of both the order of G and the order of H. So then from there, the order of an element is the least positive power that you can raise it to and get the identity. So the order of G, H, that must actually be the least common multiple of the order of G and the order of H. So I hope that idea makes sense to you. If you want more details, you can read about it in the textbook. Okay, so now let's do an activity here which references that theorem. So go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go ahead and go over the answers here. So part A is Z9 and the direct external product with Z10. Is that a cyclic group? Answer using theorem 28.9. Okay, so there's actually a little typo here. This is supposed to have a closed parentheses there. So is this a cyclic group? So in order to figure out if it's a cyclic group, we need to actually find a generator for it. So the element 1 generates Z9, and the element 1 also generates Z10. In fact, it'll generate any Zn group. So the natural kind of choice here for what the generator should be would be 1, 1. So we can just check if that actually generates the group or not. So let's just check. So let's call it A equal this element here. So 1 in Z9 and then 1 in Z10. So we're going to use this theorem to figure out what the order of this element actually is. So the order of 1 in Z9 is 9, because that is the smallest number that you can multiply it by and get 9. And the order of 1 in Z10 is also 10, because that's the smallest number you can multiply it by and get get the identity. And it's also because those are the elements that generate those groups, so their order must be the size of the group. So anyway, then what we can say here is that using this theorem, so by theorem 28.9, the order of 1 in Z9 and 1 in Z10 should be the LCM of 9 and 10. So the least common multiple of 9 and 10. What is that? Well, they don't share any divisors in common, so it's just going to be their product, 90. And then also the order of Z9 direct external product with Z10 is also 90. We talked about that in a previous activity, that you just multiply the group orders together. So, in conclusion, if you have a group element whose order is the size of the group, then it must generate the group, because it generates something, and that something is a subgroup of the group, so it must be the whole group. So that means that the cyclic subgroup generated by this element is the entire group. So I'm getting lost in this notation here. Okay, it is this entire external direct product. Okay, now does Z9 external direct product with Z10, does that contain an element of order 6? If yes, find such an element. If no, explain why not. So to find an element of order 6, we would want to make it up of an element from Z9 that had order 3 or 2, and then another one from Z10 that had order either 3 or 2. So I think in Z9 the element 3 has order 3, and in Z10 the element 5 has order 2. So we can use those. So let me just state that. So the order of 5 in Z10 is 2, and then the order of 3 in Z9 is 3. Nope, like that. So the order of this element, 3 and then, nope, 9, and then 5 in Z10 will be the LCM of 2 and 3, which is 6. Okay. All right, so one last activity to do with external direct products. So in this activity, you're going to build up the way that you can make an external direct product from more than 2 groups. So read through the directions there carefully and go ahead and pause the video and try this activity, and then we'll go over it. Okay, let's go ahead and go over this. So first of all, show that G1 external direct product with G2 external direct product all the way up through Gn is closed under its operation. Okay, so to do this, we need to take 2 elements from this thing and show that their product will still be in it. So let's just call the 2 elements, I don't know, x and y. So let x and y be in this big external direct product. Gn. Okay, then x and y must be in tuples, so x is going to be equal to, let's call it, I don't know, a1, a2, dot, 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 up through an, and y is also going to be an n tuple. So let's call it b1, b2, dot, dot, up through bn. For some, let's call them ai and bi, so we don't have to write it a million times, which are going to be in gi for all I. Okay, so doing it with the i's there just saves us from writing the same thing over and over again with a 1 and then with a 2 and then with a 3 and so on. Okay, so then what happens when we multiply them together? So if we do x times y, this is going to equal a1 b1, comma a2 b2, comma dot dot dot, all the way up through up through a n b n. Okay, and then how are we going to show that this is actually still in the external direct product? Okay, so we could say that since ai, bi are in gi, then ai times bi is also in gi, because gi is a group, so it's closed. So that means that xy is going to be in this external direct product of g1 through Gn. Okay, so it is closed. All right, now let's look at the second part. For each I, let EI be the identity in GI. What is the identity element in G1 external direct product up through Gn? Prove your answer. Okay, so not very surprisingly, the identity here is going to be just the ordered tuple that contains all of the identities from the subgroups, or the parts of the external direct product. So let me just write that. The identity is E, which is going to be equal to E1, comma, E2, comma, up through En. Okay, and then to prove that, let's just call it, I don't know, G1, G2, up through Gn be an element of this external direct product. Okay, then what happens if we multiply E times that? Then we get the following. So if we do it, let's see, actually let me call this by a letter. So let this be like X, I guess. Then if we do E times X, that's going to be E1 times G1, and then E2 times G2, and then so on and so forth up through En times Gn, okay, which is just going to be equal to G1, G2, up through Gn, okay, which is just X. And then if we do it the other way around, X times E, so it's just going to go the same way, except in the other order. So the E1s will be at the end, and then G2, E2, up through Gn, En, and that's also just equal to G1, G2, up through Gn, which is also just X. Okay, so that is indeed the identity. Okay, part C, show that the operation defined above is associative in G1, G2, the external direct product of all of those. Okay, so associativity, so we're going to have to pick 3 elements. So let's call them, I don't know, X, Y, and Z. So let X, Y, and Z be in this external direct product. Okay, then we have that X can equal, I don't know, A1, A2, through An, and then Y can equal B1, B2, up through Bn, and then Z can equal C1, C2, up through Cn, where Ai, Bi, and Ci are all in Gi for all I. Okay, so we've defined our 3 elements that are in this external direct product, and now I just have to multiply them with the parentheses in both places and show that that is the same. Okay, so then X times, just do Y and Z together first, is going to be, so this will be, let's see, I'll write the X part by itself, and then I'll do Y and Z all in one fell swoop. So this will be B1, C1, and then B2, C2, up through Bn, Cn. Okay, and that is the same as, if I put the A's in there with them, A1, B1, C1, A2, B2, C2, and so on and so forth. Okay, and that is the same as, so if I separate the C's out, so I can leave the A's and B's together and then separate the C's. Oops, no. It'll be A2, B2, An, Bn, and then, okay, so now I'm going to write the C's on their own part. Okay, and this is X and Y together, and then Z by itself, like that. Okay, so it is associative. All right, show that each element in this external direct product has an inverse that is also in the external direct product. Okay, so this is not very hard. It'll work just like it does for 2 groups, just a lot of notation. So let's let X be in the external direct product. Okay, then x is equal to some, I'll call them g's this time, g1, g2, up through gn, then there exists an inverse for each one of these. So there exists gi inverse for each gi in big GI, which will also be, maybe I should also say that. So this GI inverse will be in GI for each little GI in big GI. So the following x inverse equal to g1 inverse, g2 inverse, g3 inverse, so on and so forth up through gn inverse, will also be in the external direct product. And so I've just defined this element, but I haven't actually shown that it is the inverse of x yet. So I need to do that. So then x times x inverse will be the following. It'll be g1, g1 inverse, g2, g2 inverse, dot, 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 up through gn, gn inverse. So that will be E1, E2, so the identity element in each of these little groups. Okay, and that is the same as the following. So it's also the same as doing G1 inverse first and G1 second, G2 inverse first and G2 second, and so on, up through Gn inverse first and Gn second. And that is x inverse times x, so that is also the identity. All right, so this shows that they have inverses. All right, and then finally, what conclusion can we draw about the set G1, G2, dot, 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 the external direct product of all of those? So we showed that it's closed. We showed that it is associative. We showed that it contains the identity. And we showed that it contains inverses. So it's a group. Okay, so let's start into internal direct products in groups. So we call the external direct product of G and H an external direct product because it's constructed outside of both G and H in the sense that nothing from either group interacts with anything from the other group. They just stay in their own lane, they stay in their own little part of the tuple. But what if G and H were actually subgroups of the same group? Then we could define a different type of product with an operation that would allow their elements to interact. So that's exactly what an internal direct product is. So suppose that both K and N are both normal subgroups of a group G, and that their intersection, K intersect N, is E, just the identity. Then the set Kn, which is defined like this, so it's defined exactly like what it looks like. It's the product of all of the elements from K with all of the elements from N. That is actually a subgroup of G. I think we actually looked at that once. I don't remember if it was a homework problem or a practice test problem, but I think we've done that before. So this subgroup is denoted like this. This is a really unfortunate notation, but that is how it is denoted, and that is called the internal direct product of K and N. I really wish that they would not denote it like this and that they would just leave it as K times N, just sitting next to each other with no symbol in between, but we're going to denote it like this. It is the same symbol as the Cartesian product, but confusingly, the elements are not from the Cartesian product. So that actually kind of makes it even worse. It looks like the Cartesian product, but it has nothing to do with it. Yeah. So anyway, I'm not happy with this notation, but that's what your book is using, so we're going to go with this. So that is the internal direct product of K and N. Okay, so let's look at the formal definition here. Definition 28.12, let G be a group with identity E, and let K and N be normal subgroups of G, such that the intersection of K and N is just the identity. Then the internal direct product of K and N is the subgroup. It's K times N, where it's just the product of all the elements in K with the elements in N. So caution here is just to remember that, like I said earlier, some authors actually define this K times N as the external direct product of K and N, and the notation K times N also refers to the Cartesian product of K and N, like I said. So just be really clear that you know what an author means in the context, and I'm going to do my best to read this aloud as K times N and not K cross N, because there's no crossing going on at all. When you talk about the word cross, like for Cartesian product, it refers to the fact that if you draw a Cartesian product in the plane, you're actually like drawing the sets that like cross angles to each other, and you can make the points from that. But that's not happening in this case at all. So I'm going to try to read it as k times n. Okay, so one interesting thing to note about this is that external direct products are actually internal direct products, and they are that in the following sense. So remember that we found these subgroups before in the external direct product of G and H. So I'm going to call this one G prime. So G prime is the external direct product of G with just the identity from H, and then H prime is going to be the external direct product of the identity from G with the group H. So those are both actually subgroups of the external direct product of G and H, and in fact they are normal subgroups, although we haven't proven that, but it's one of the exercises for this section. So you might see it as a homework problem. So these two subgroups, they actually generate all of the elements of the external direct product in the following way. So if you have any element, any ordered pair like that, GH, in the external direct product of G and H, you can actually write that ordered pair in the following way. So you can write it as G with the identity from H, and then the identity from G with H, and then if you multiply those together, you will just get GH. So that means that every element of the external direct product of G and H is of the form little g prime, little h prime, where little g prime is in G prime, or rather in G, sorry, and h prime is in H. So that's kind of interesting. Furthermore, the only element that is in G prime and in H prime is the identity element for that external direct product. So what this means is that the external direct product of G and H is always an internal direct product of G prime times H prime for those two subgroups, G prime and H prime, that we found before. And those two subgroups, as we said previously, those are essentially the same as G and H. So this is interesting, and this is a strong connection between these two different types of products, and it has actually led to some of the confusion, I believe, in the notation and the terminology that people use. Okay, so let's do an activity here. Activity 28.13. Go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go over this activity. So the operation table is given below for U28, which is the group of units in Z28 under multiplication. So remember, the units are the ones that are relatively prime to the modulus, and they have multiplicative inverses. So our operation here is multiplication. And I've listed the elements there for you, and they're also in the table down there. So let K equal the cyclic subgroup generated by 9, and N is the cyclic subgroup generated by 13. And then note that those two, their intersection is just the identity. Find the elements of K times N, and then write the operation table for K times N. Okay, so firstly we need to actually find the elements for K and for N. So what are the elements in K? Oops. So the elements in K are going to be the following. So this is generated by 9, so that means it's going to be all of the integer powers of 9. So first of all, there's 9, and then there is 9 squared. If you do 9 squared, you can check in the table down below. It's actually right here. It's 25. And then if we do 9 cubed, that is actually going to be 9 times 9 squared, so 9 times 25. And we can check that one in the table too. It's right here. So that is 1. So that's going to be the last element that's in there. So it's just these three elements, 1, and then 9, and then 25. Okay, and then what is N? So N is the cyclic subgroup generated by 13. So that is going to be all the integer powers of 13. So that's going to be 13, and then 13 times 13 is, it's right here, it's 1. Okay, so it's just those two elements right there. All right, so then the elements of K times N, the internal direct product. So that is just going to be the following. So K times N. So just to remind you, that is all of the little k's times the little n's, where little k is from big K and little n is from big N. Okay, so we have 3 elements in one group and 2 in the other, so we can do this 6 different ways. So if I take all the 1s times everything that's in N, so this is 1 from K times everything that's in N, and then I can do 9 from k times everything that's in n, and then I'm going to do 25 from k times everything that's in n, and then I just have to figure out what these all actually equal. And they might not actually be different from each other, I don't know. Let's find out. So, okay, so this one is going to be 13, and then this one is obviously 1, and then 9 times 13, I'm going to use my table for that. So 9 times 13 is right here, that's 5. And then 9 times 1 is 9. And then 25 times 13, let's see, it's right here, that is 17. And then finally 25 times 1 is just 25. Okay, so that is k times n. And then the operation table for k times n. So the operation table, I'm not going to do the whole thing. I'm just going to show you how you would make it from this table. So basically you would just cross out everything that's not in k times n. So like we don't have 3, so that wouldn't be there. We don't have 11, so that wouldn't be there. And then what else do we not have? We have 13, we don't have 15, and we have 17, we don't have 19, we don't have 23, and we don't have 27. So we just cross out all those columns and rows basically, and then that would leave you with the operation table. So I think this is a faster way for me to do it for sure. I don't want to make a 6 by 6 table. Let's see, 19 and 23 are gone. And then 27 is gone. Okay, so that'll be it. And then if you look at the entries that are left there, yeah, you can actually see that they do have the same kind of Sudoku effect. All of the entries in the table are only those from k times n, and they appear exactly once in each row and column. Alright, so I think that's all that we have time for today. So we'll finish up investigation 28 next time, and we'll start into investigation 29. See you guys later.